I'm Gerard Gorman, and this is our presentation, Performance Portable High Performance Software for Seismic Imaging, leveraging the power of DSLs, Symbolic Computation, and Python. So let's start off with what's the big picture here in terms of the problem. What are we trying to do? Well, primarily the motivating problem is hydrocarbon exploration. So this is really heavily dependent upon state-of-the-art 3D seismic imaging techniques to make informed decisions. So basically, simply put, like where's the oil? And to get you an idea of like how important it is to be able to answer that question, like roughly the cost of drilling a new well is in the region of, I say, 100 million. Like, roughly that number of zeros. And actually, frequently these wells, when they're drilled, are discovered to be dry. So there's a massive loss of efficiency there. So thus the interest in developing good imaging technology. It's also used during the life cycle of a reservoir in terms of getting the most out of it. Like it's evolving over time, the fluid is changing within the reservoir. You need to be able to monitor that. And I think increasingly as we go forward, like as we go, areas such as CCS, like carbon capture, utilization, and storage, are becoming important. We're going to be able to want to do continuous monitoring of carbon dioxide stored in reservoirs under the ground and make sure that they're stable and they're not escaping. Now, as we start actually moving towards a solution, so how do we create really good images? Well, currently, variants of FWI and RTM are the best methods for creating images as a subsurface, but they're very computationally expensive. So typically they involve processing like terabytes to petabytes of data just for a single survey. And it's, I believe, the largest application of HPC in the oil and gas industry. And the core of all of these methods is solving the wave equation, or some form of the equation, a wave equation. All that really changes is the fidelity of these equations, like basically how much physics you're resolving. And of course, you're solving the adjoint of those using finite difference methods. Of course, this finite element and other methods are being researched, but in terms of production, everything is explicit finite difference methods. And these methods are under constant innovation. This is a very hard problem. People are constantly coming up with algorithmic tricks to make it go better, to make it run better, give you more accurate solutions. And this results in regular software updates. Now, in terms of actually developing the software, it's a bit like painting the Golden Gate Bridge. It's just a continuous process. Like say, every little bit of because the computation is so huge, and like its cost is like these are very expensive calculations to run on a supercomputer or cloud. So even a 10% increase in performance, like is really valuable just in simple dollars. There's also a huge cost to porting and optimizing the software from one architecture to another, and particularly in the programming model changes. Like it's often remarked that like if you think that HPC buying the hardware is expensive, and you see how much software development costs. Like so, this is a massive cost. Like this constant cycle of development. And then there's also, as I mentioned earlier on, like people are constantly making algorithmic like innovations to get better solutions. So there's this constant stream of prototype code coming from the researchers, and these need to be productionized by like the HPC experts that actually know how that will be focusing on production software, production standards that's also optimized for different flavors of HPC. But this is problematic as well because there isn't that many coding ninjas out there. And then, of course, there's the cloud. And so this is just yet another rock that needs to be dealt with. So again, all of this is a lot of work. So what's the solution? So simply put, like say, we've developed the Vita to make it easier for scientists and engineers to write high performance and portable software for CPUs, GPUs, and whatever architectures around the corner. And I think this is very much in the spirit of thinking about automation or raising the layer of abstraction to another level. So rather than thinking about writing your code in Fortran or C or CUDA, you instead write it at a much more high level, and so that you can develop code a lot faster. So, like, what does traditional HPC software development look like? Well, it basically boils down to your PDE there on the left-hand side, and then this gets translated over into like impenetrable code by the ninjas. And there's issues here in terms of the cost. This is proprietary code, so everyone incurs the cost. And there's also then an opportunity loss, because you have actually separated the experts who understand the application, the problem, the mathematics, and those who actually are implementing in software. So you have disconnect, which means you're losing out on perhaps further optimizations. What you're doing with any domain-specific language, like the Vita in particular, is well, first of all, we've embedded this in Python, so that comes with a number of advantages. Python is a very easy language to learn. It's very popular, so you can have a reasonable expectation that like geophysicists will be comfortable with it. Your domain scientists will be comfortable with it. So it's embedded within that, and then we have subclass SymPy. So I think SymPy, is one of the maybe the hidden gems of computational science. Like, it's a symbolic math library. So this is what we build on top of to be able to express everything symbolically. So that's that equation here, where I've written EQN equals A multiplied by, and so on and so forth. You can see that pretty much looks like the right-hand side. So we can now actually start writing code that looks precisely like the math. And then that's all that we write. Like I said, then it's up to the Vita compiler. So we have written our own compiler then for our domain-specific language that's able to take that code. It's able to take the overall problem specification, and then it's able to automate the generation of the low-level code, whether it be C, OpenMP, OpenACC, and so on. The key thing here to remember is that finite differences was developed nearly 300 years ago, and so we know the rules quite well. We have for quite some time, and also there is a huge amount of effort there's already decades of effort gone into understanding how to do polyhedral type optimizations or different types of fancy optimizations for structured code. So really, you're bringing these two things together and you're simply automating it. There's no magic here. So in terms of what is features, well, the key thing and its objective here is to enable developers to write finite difference at the same level of abstraction as a math. So in other words, we design a language whose top level of abstraction is the math, plus a few other lines to actually to do some problem specification, as in which source and receivers and other stuff that you need to set up a real life problem. And then the compiler uses symbolic computation basically to lower that specification into intermediate representations, and then it's able to apply lots of rules and do lots of standard compiler analysis to understand what's the optimal way of generating code given that input. And scientists, so basically scientists then get retrained to write performance portable software in symbolic math and not loops. So this is popular for a number of reasons. So researchers are now coding in Jupyter notebooks, which are also hugely popular, and so it's facilitating quick prototyping. But it's wrong to think of the Vita as just a thing for prototyping. It does that very well, and lets you turn around, do algorithmic exploration very quickly and do interactive computing. But it's the same code then when you actually want to turn it into production. It's already running. It's already generating high performance code that is generally very close to what a guru would be able to write if they hand wrote the code and hand tuned the code, and it's often faster. So one of our commercial users, they're currently running the Vita 24/7, and it's about 10 times faster than their previous code. In terms of features, like it's open source, so I think that the open source is an important aspect here. Like our vision and what we've been trying to do is to build up a community around this, and open source community, so which is unusual for the oil and gas industry that mostly deals with proprietary codes. And so we've got about a community of about 500 people on our Slack at the moment. And it's to encourage people to use, to adopt, contribute, and provide feedback, and so on and so forth. And there's also a spin-out company then, and we're using an open core business model, and that's just to provide commercial support to companies because they won't use open source if no support structure exists. Again, Python was an important decision because it makes it easy to learn, interoperable with the ecosystem, including ML, interoperable with other languages. Like I seem to be using the word interoperable frequently, but this is really crucial, I think, in modern HPC. In terms of supported backends, it's C, primarily C, OpenMP, OpenACC, MPI. And in terms of CPUs, Intel, AMD, ARM, GPUs, NVIDIA, AMD. So we're aiming to cover all architectures. And really critical to making this work is a strong emphasis on best practices software engineering. So we look upon things like CI/CD and code verification, like a code review of all PRs. This is not seen as an inconvenience, rather it's seen as actually, all developers appreciate it as being a good way to accelerate the development. And because basically their code doesn't get broken at some other point in time when they're looking someplace else, and they know that it's working because they edit a test to make sure that it will continue to work in the future. Now, primarily we are focused on explicit finite difference schemes, simply because that's pretty much all that's used in production. But there would be no problem to extend that, and then various other support like sparse functions, subdomains, staggered grids, and much more. So quite rich. And I think a key thing, I think, for all people developing DSLs and bringing DSLs into the mainstream is they can't be black boxes. And I think a lot of the DSLs in the past failed because the abstraction has been too rigid. So then when you pick them up and you start using it, but then you want to do something slightly different, because like in engineering firms, there's always going to be something slightly different. And then it was on a platform that's very hard to change. So I think an important decision was to make sure that we had built in a JIT backdoor. So that basically means we generate very well formatted, human readable code in C or whatever the intermediate language is, so that like a guru can always come in and actually start at that level in terms of extending the code if they need to. Something else that we recently released is now that everything has become programmatic and it has become much easier to implement all of these operators. We are creating or building out a matrix of benchmarks of like every seismic operator across all computer architectures. And so we have got an on-prem cluster that's growing, that's building up all different types of architectures. And then we're just automating, running all of these standardized benchmarks through that in a consistent way. And it does two things as well. It facilitates, of course, comparison across architectures, but it also tracks performance in history. So we know that we're monotonically improving the performance of the code. And so every change is making the code go faster rather than the other way around. So here's a sample. So if you if you want to see more details, if you go to the DeVito website, it'll have the details in all the glory. But this is there's a lot of data here. But just to sample one, what you can see down here on the left hand side is all the different architectures. So there's A100s, there's 3090s, Intels, AMDs, MI50s. And basically all these now can be compared, apples to apples comparisons can now be done between all of these. So in this particular case, we're looking at isotropic acoustic, which there's various other benchmarks there, including TTI. So one of the new architectures that we're going to be adding to the cluster very soon is the A64FX. But Bristol kindly allowed us access to their system so that we could have a quick look to see what the performance was. And say out of the box, we were getting 4.28 gigapoints per second. So this is, if you like, a metric that's commonly used in seismic, because rather than gigaflops can lie to you. Because what we've demonstrated with the Vita, maybe an interesting observation, is very often when we apply flop reduction optimizations, you can see your runtime, so time to solution, is decreasing, while your number of flops is also decreasing, which is maybe not surprising. But like but if you took major gigaflops, your gigaflops might be increasing. So because you have got these this types of optimizations, gigaflops is typically the wrong thing to look at for an application. But instead here, this measures the number of gigapoints. So that basically measures how much data we're processing. So at the moment, it's coming out at 4.2. So on this graph here, it's basically like currently it's just around, just under the Sky Lake. Now, what we would be expecting, because the A64FX has got a much higher bandwidth, we should be getting significantly better results, because we know that the isotropic acoustic wave equation is memory bound, so it follows. But again, like just to emphasize, this is an unoptimized and out of the box result. So to wrap up, DeVito is a finite difference development platform, and it's important to recognize it's actually part of a wider set of DSLs are cropping up, such as Phoenix and Frederick, for finite element methods, for example. And the level that it's pitched at, like it's primarily targeted at like scientists, engineers who are going to use this as a platform to develop end user applications. So it shouldn't be considered to be an end user application in itself. It's only giving you the platform, like a development toolkit for you to develop standard applications. Like currently, it's heavily used in seismic imaging. So we have already implemented a wide range of operators: acoustic, TTI, elastic, viscoelastic, and so on. So all the major operators are like typically used in seismic imaging today. But also because it is primarily a mathematical programming platform, we're looking at what other areas where it can be applied and have high impact. So one of these collaborations is with Lewis, focused on medical imaging. So he had a talk at GTC this year on GPU accelerated neuroimaging with DeVito. So previously they had published a paper in Nature where they demonstrated that FWI could also be used for using acoustic ultrasound to image the brain. And we helped them integrate DeVito, and they got a 20 times speed up, again, out of the box. So we're also as prototypes, we've developed the DeVito core for PyTorch, because like the type of the computational pattern that's involved in very large convolutional networks. So you imagine large convolutional networks that require distributed memory. It's pretty much identical to the type of programming patterns that are already available in DeVito or supported by DeVito. We're developing some CFD problems. So it's on a roadmap to include support for implicit solvers. Most likely this would be done through PETSI using matrix-free callbacks. We also have an example with Black-Scholes for finance. And virtually like all partial differential equations on unstructured grids that are stencil-like. And of course, we're continuing to support more architectures. So acknowledgements. So it's always hard to get funding for open source. It's a big step for lots of companies. So big thanks to all the companies that did support this open source initiative. In terms of both finance, in terms of hardware and engineer support and all the rest. Many thanks to our community of users and contributors, and there's a full list of releases and more importantly, a list of contributors if you go to the GitHub website. Thank you.